Hello everyone, hope everyone is doing well. In this video, we're going to look at how to evaluate our hypothesis at different critical values. Now, this is one of the exercises we did in an earlier lecture, and we looked at if a training for a bank has reduced customer wait times. And so we found out that the customer waiting time of a bank originally was 5 minutes. So this is my mu, and so this value is my mu, and I have this value turning out to be my population standard deviation sigma. So in an effort to reduce wait times, bank implemented a training sessions, and then after it was done, I have n of 35. Now my new mu, or x bar from the sample, is 3.8 minutes, and sample standard deviation is 1.8 minutes. Now, however, since we have population standard deviation, so we will be using the z-stat to do our analysis. Now, we have to test if the waiting times have decreased, and my alpha, testing it at alpha at 5%. So whenever we do the problems like this, we said that the first step is to state the null and alternate hypothesis, which we have done. You can write it in two ways, in sentence form like this, or in basically equation form like that. So in our case, the null is that the mean is, or the population mean is equal to or greater than 5 minutes, and the alternate is it is less than 5 minutes. So if we drew the distribution here, it would look like, basically, if this is my mean, since I want the waiting times to be reduced, so I would like any number beyond a certain value to be in the rejection region. So this is then going to be a left-tail test. So after that, I collected the data, so which is my step 2. I have collected the data, and my x bar is here. My sigma is given. Since I have population standard deviation, I don't need to use the sample standard deviation right here. So I'm going to use the population standard deviation and n. Then in my third step, I will find the z-stat, and this is the formula of z-stat. So my numerator is going to be 3.8 minus 5. Denominator is 2 divided by the square root of 35. And I find that my z-stat comes up to be negative 3.54. So the first 3 step is going to be the same for no matter what level of alpha we use to analyze or evaluate our hypothesis. Now in the fourth step, if my alpha is 0.05, remember that this is a one-tail test, so my critical value I'm going to find with this formula. And so my critical value would be negative 1.644. So it is negative 1.644. So from here, I can see my z-stat, it is way out here, but my critical value is here. So it is definitely, my z-stat is in the rejection region. I could say since it's a left-tail test, my z-stat is less than the critical value, so we reject the null. Or I could just get rid of the negative sign and say that the absolute value of z-stat is greater in magnitude than the absolute value of the critical value of z. Basically, I'm saying once you take away the negative signs, the z-stat is greater than the critical value. So we reject the null, and the waiting times fell. Now let's say we want to look at the p-values. How to evaluate the hypothesis statement using the p-value. So let's say we want to find, this is the value, this is what we use to evaluate it. So whatever the alpha is, if for the p-value I calculate is less than alpha, we reject the null. And conversely, if p-value is greater than or equal to alpha, we do not reject the null. So the p-value, given the formula is here, we take the z-stat, so norm.s.disc, the z-stat, and comma true. So we find that my p-value here that I calculated is less than alpha. which is 0.05. It is way less than alpha. This is almost close to 0. So therefore, we will reject the null. Now let's say, instead of all this, instead of evaluating at 95%, or sorry, at critical value of 0.05 or 5%, we are going to now evaluate at 10%. So let's say my alpha is 0.1. Everything else remains the same. So steps 1 through 3 should remain the same. The only thing that would change is step 4, which is going to be alpha is now equal to 0.1. And if that's the case, then I will change this formula. This will be now at 0.1. So the things that we will change, I will just highlight that, is we're changing the critical value right here. And also this critical value. So this is now telling us that, okay, we are now evaluating at this critical value. Now the z-stat is at 3.54. Now if I draw it again, based on my diagram, I can see that again, just like before, this is my z-critical. It is going to be 1.64 negative. And my z-stat is way out here. So then we can say that the absolute value of z is greater than magnitude than the critical value, so we reject the null. The waiting times fell. Now if I were to find the p-value of the z-stat, what I would do is basically calculate the p-value, which is right here. So the p-value would be, we would do the same thing here. We find the p-value is this formula. So we take this z-value and find the p-value of that. Now we find that the p-value is less than alpha, which is, in our case, 0.1. So we reject that. Now, if I say next, let's say if I were to find the case where alpha is 0.01, then everything else again stays the same. I just need to update my alpha down here to 0.01. And so my critical value is going to change to negative 2.32. So if everything else stays the same, then instead of z-critical to be 1.64, z-critical now will be equal to negative 2.32. But my z-stat is negative 3.54, which is way out here still, so we still reject it at the 0.05 critical value. Here too, the p-value stays the same. We are now comparing this value with 0.01. So we will say that the p-value is less than alpha, which is 0.01. So we reject the null. Now let's look at this was the left tail test. Now let's look at what will happen if we are not given the population standard deviation. Let's say we do not have this statement. So this is missing from us. So if that's missing, then we don't have sigma. So if we don't have sigma, and let's say we start at 0.05 again, if the population standard deviation is not known, then we are going to use the t-stat. And so for the t-stat, we don't have sigma, so we are going to use S bar, which in our case is 1.8. And so once we have this number, we now need to change this to t-stat. And my t-stat is, updating the formula, it's t-stat is x bar minus mu divided by, it's going to be S bar over the square root of n. So my numerator is still 3.8 minus 5, but my denominator now will be 1.8 divided by the square root of 35. So I get 1.8 divided by the square root of 35. And my z-stat, instead of z-stat, this will now be the t-stat. So my t-stat is 3.94. Now to find the critical value at alpha equals 0.05, I would basically change this to t dot inv. The probability is 0.05. The degrees of freedom is going to be 35 minus 1. And so I get a value of negative 1.69. And so now my t critical value will be negative 1.69. So again, I would say that the absolute value of now, instead of the z stat, I will say the absolute value of the t stat is greater than in magnitude than the critical value of t. So we reject the null and the waiting times fell. Now, if I were to do the p-values for that, we would have the same answer. The p-value here would be of this t-stat, which would be t.inv. Actually, sorry, it would be t.dist would be x, comma, the degrees of freedom will be 35 minus 1, and cumulative is true. And we compare this to the alpha value. So the p-value, my alpha is 0.05. So the p-value is less than alpha. And so therefore we reject the null. Now again, if we were to do this at 0.1 or 10%, as we said before, everything else will remain the same. We just have to change the critical value, which is now 0.1. And so my critical value will be 1.30. So again, this critical value will be updated to negative 1.30. So again, we plug it in here and we find that the p-value stays the same, but we have to update our alpha. Our alpha has to be less than 0.1 for us to, or our p-value has to be less than 0.1 for us to reject the null, which it is, so we reject the null. Now let's say if I were to do at 0.01, then everything else again remains the same. I need to just update my alpha to 0.01. And so this one goes to 0.01. My t-value, this one, I update that to 0.01. Now my critical value of t is negative 2.44. So again, I reject the null. P-value stays the same, but I will update this to 0.01. And so the p-value is less than alpha, so we reject the null. So this shows us if we have both the population standard deviation given or not, basically everything, all the steps follow the same no matter what the critical value is. Only in step 4, it's where we find the critical value, that's what we update. And so this is the thing we update, and then we compare it with our t-stat, or we update our z-critical and compare it with the z-stat to basically figure out if we reject the null or not. Now let's look at our case where we are looking at the right tail test. So again, let's start with alpha is 0.01. So our alpha is given at 0.01. The mean is 75. And we are not given the population standard deviation, so we will start with the t-stat. So we talked about this problem before in a previous lecture, so I just copied and pasted it here. So in this case, we can see that, so in our case, if the null is less than or equal to 75, we are okay. We do not reject the null. This is a testing format change, and leading to that change, we want to see if the mean score improved or not. So in our case then, based on the null hypothesis, if this is my mean, any number greater than this value, this is the critical value. If my z-stat or t-stat falls in this region, then I reject the null. So that's the rejection region. So we have this is my mu, this is my n, and this is the x bar that we have. And I have an s bar here, and I'm testing it at alpha equals 0.1. So in step 2, I wrote down all the information I needed, and in step 3, I calculated the t-stat. So my numerator is 82 minus 75, which gives me 7. Denominator is the sample standard deviation, which is 2.4 divided by the square root of 60, which I get that number. So the t-stat is just 7. This is going to be basically 7 divided by 0.309. And so I get out that number. Now, what is going to be my critical value of t at alpha equals 1? This value, if you remember from before, whenever we measured, our Excel measures the t-stat, or the critical value of t, it's usually from the left to the right. So it's always given a negative value. So that's why we add a negative value in front to give us the actual value, which is going to be, for 10%, it's going to be, t critical will be 1.29. I could also use another formula, which basically is t dot inv dot. And so I will compare my critical value of t with the t-stat, and I find that my t-stat is way higher. So we are going to say the t-stat is greater in value than the critical value of t. Here everything is positive, so we don't need to mention absolute value, so we reject the null, and the test scores have improved. Now let's say I'm looking at p-values. So in my case, the p-value will be, I have to do 1 minus the t-dist. So if I want to find the p-value, I either do 1 minus t-dist of the t-stat, and this is going to be my degrees of freedom, comma true, saying that it's cumulative, or I could use this formula, t.dist.rt, and this is my t-value, and it's going to be 60 minus 1. The reason is, whenever Excel finds the area, so whenever it does t-dist, as we said, whenever we use distributions, it always finds the area to the left. But in our case, this is the non-rejection region. We want, if this is my critical value, we want this to be the rejection region. So everything to the right, this value should be the rejection region. So that's why we do 1 minus the t-distribution to find this value, this red region, or we can use this formula, t.dist.rt. And so we will say that the p-value is less than alpha, which was 0.1, so we reject the null. Now let's say if the p-value alpha is 0.05, then again, everything else stays the same. We just need to change this critical value, which is down here. So this is what we need to change, this value and this value. So this value becomes, if I'm changing it to 0.1 or 0.05, it has to be 0.05, and this value basically becomes 0.05. So then my critical value is now 1.67. And my t-stat is way higher, so I would just say that t-stat is greater than the critical value. So we reject the null. Here too, since the p-value stays the same, I just need to update what the alpha is. So the alpha is, we used at 0.05. And I still find p-value is less than alpha, so we reject the null. Now if I were to change this alpha to 0.01, I would do the same thing. I would change this alpha to 0.01. And the t-value would be now 2.39. So my critical value would be updated to 2.39. And I would say that the t-stat, same thing goes here. P-values, everything stays the same, but I need to just update my p-value to 1.01. So this is what I would do for testing it for the t-stat. Now let's say that the population standard deviation is actually given in the right tail test. So everything else remains the same. Let's say we just add another line. Let's say the population standard deviation is 2.7. So now we would update this and we start, let's say, with alpha at 0.01. Now we have sigma, which is 2.7. And we now have a z-stat. So z-stat, everything else remains the same. We just need to make this into sigma over square root of n. So my numerator stays the same. My denominator now will be 2.7 divided by the square root of 60, which becomes 20.08. So instead of t-stat, this will be now a z-stat. So we are now going to find the critical value of z at alpha equals 0.01. And for this, I would do z norm dot inv, and everything else remains the same. However, norm.inv would give me the negative value, so I still need to put the positive value. Actually, I need norm to make it easier, norm.s.inv. So I would get 2.32 is the number. And so I would say that z-stat here is greater than the critical value of z. So we reject the null and the test score is improved. For our p-values, we no longer need t.dist. The p-value would be equals to norm.s.dist. This is my z-value. Cumulative is true. But if I write this, I will get a 1 value, which is because it's measuring the area from left to right, just like with the t-value. So when I am drawing a normal distribution here, if this is my z-value, which is 20, so this formula is basically finding all the area of all the region to the left of z. But I want the region to the right of z, so I will update this formula to 1 minus. Now, for t-stat, as we saw, we had a right tail formula, but for z-stat, we do not have a right tail formula, so we are just going to use 1 minus that. And we will say the p-value is less than alpha because it is essentially 0, so we reject the null. Now, if we move this to 0.05, again, we have everything else stays the same. So now we just need to update the t-value or z-value here to 0.05. And this becomes 1.64. So this is going to be my critical value of z, or the z critical value. And I'm comparing it with the z-stat, and the statement goes. For the p-value, this part stays the same, but I am comparing this p-value instead with 1% alpha. It's now going to be 0.05. And we reject the null. Lastly, if I do alpha of 0.1, then my critical value of z at alpha equals 0.1, I need to update that to 0.1, and I get 1.28. So this number will be 1.28. Just a recap, there is a negative sign in front of here because if I did not put the negative sign, I would get negative 1.28, which would be this one. But since the value is, the z table or the normal distribution is symmetric, so negative 1.28 basically exactly mirrors positive 1.28. That's why there's a negative sign in front of the normal distribution formula. So everything else follows. The z-stat is greater than the critical value, so we reject the null. Here too, we find first the p-value, so that doesn't change. We just update this number. The p-value is, or the alpha is greater than the p-value, so we reject the null. Hopefully this was helpful, and it shows you how you can answer different hypothesis testing questions at different critical values. You can use either the z or t or the p values to show if you reject or not reject the null hypothesis. Have a good day, and I will see you at a later video. Goodbye.